In this video, I'm going to teach you about enolates. They're very important for a whole host of reactions. Let's jump right in. In a carbonyl compound, the carbon atom right next to the carbonyl is called the alpha carbon. And it's special because if it has a hydrogen on it, those hydrogens are very acidic. They're easily pulled off by a base, so I might have something like hydroxide. Can come pull off the H plus and leave the electrons behind on that carbon to make this. So I could have a carbonyl with whatever on it, and on the alpha carbon I have a lone pair of electrons with a negative charge. And that's a particularly stable negative charge with that lone pair of electrons, because I can draw resonance forms where these electrons could be pushed all the way up to that oxygen. It starts with 2 lone pairs and now has 3 lone pairs, so it has a negative charge. Double bonded to this carbon. So because I can spread that negative charge over 2 atoms, the carbon and the oxygen, that's a pretty stable negative charge. So it's easy to pull off that proton because I make things that are pretty happy. Now this compound right here is called an enolate, this intermediate, this negative intermediate. And here's where that name comes from. So if I have a carbon double bond carbon with an alcohol on it, alkenes end in -ene, they're enes, and alcohols end in -ol, so this is an enol. So if I have a double bond with an alcohol on it, that's an enol. And if I pull that proton off to make a negative oxygen, that would be an enolate. 8 means negative charge. So here I have a double bond with a negative oxygen. That's why I have an enolate. But whenever we make enolates, there are 2 resonance forms for it. But I want you to focus on this resonance form. This is the one I think, even though the name comes more from this form, this is the form that makes the most sense when it comes to the chemistry. So now that I have a carbonyl, let's put an R group on it. I have a negative carbon and whatever else on it. This is a good nucleophile. It's a good attacker. It'll go attack something else. So let's look at just maybe 2 examples of what it might attack. I could take something like chlorine, Cl2, and that negative nucleophilic carbon could backside attack. My leaving group could leave. I could put a chlorine next door on the alpha carbon, next door to the carbonyl. Or it could react with bromine, and it could backside attack. That's a good leaving group. So you can halogenate the carbon right next door to the carbon, the carbonyl, the alpha carbon, with a simple reaction of chlorine or bromine. These can also do SN2 type reactions. So if I have an enolate, the negative carbon next door to the carbonyl, let's pick something like ethyl bromide, something with a good leaving group. I can backside attack, my leaving group could leave, and it can do an SN2 type reaction. So now this carbon is attached to that carbon, so it has 2 carbon atoms, an ethyl group on it. So enolates can backside attack halogens, and they can do SN2 style reactions, and they do many more reactions, which we'll get to in further videos. All right, so a quick recap. Any carbon next door to a carbonyl that has a hydrogen on an alpha carbon, these are easily deprotonated. Let me give you the 2 most common bases I find. Hydroxide is a very common base. Or you also will often see one called LDA. And I want to show you what LDA is quickly. LDA is lithium diisopropyl amide. So that's a nitrogen with 2 isopropyls on it. Diisopropyl. The amide part means there are 2 lone pairs of electrons. So this nitrogen has a negative charge. There's a positive lithium, a counter ion. And that negative nitrogen with this big bulky groups on it, it's a big bulky base, and I can deprotonate my alpha carbon. So hydroxide is very common, and LDA, you should just learn that's a big bulky negative base, which helps deprotonate these alpha carbons. Think about subscribing to the channel so I can continue to help you with organic chemistry.